Hi, in this video we are going to talk about the concrete implementation of arbitrage detection. I don't want to implement it from scratch because it would take a lot of time and basically there is no point in hard-coded something like this. The better solution would be to connect to a server or a service and download the data from there, constructing the vertex, the edges and the whole graph with the help of Java code and run the Bellman-Ford algorithm. But just for demonstration purposes, I think it's going to be okay. So the vertex class is going to be the same. We have the ID, we have the boolean flag whether we have already visited that given vertex or not. We have the min distance, which is initialized as the maximum value, basically infinity. We have a previous vertex to be able to track the predecessor, and we have a list of edges, the adjacencies or the neighbors. And of course we have the getters and setters, and in the toString method we just print out the ID. Okay, then we have the edge class with the weights, with the start vertex and the target vertex, with the given constructor which have a start vertex, a target vertex and a weight, and initialize these parameters accordingly. And of course we have the getters and the setters. The Bellman-Ford algorithm is the same. We have the vertex list, we have the edge list, we have the cycle list. We are going to put the currencies that forms the cycle in a list of vertices, and that's called a cycle list. In the constructor we have the vertex list and the edge list, and of course we have to instantiate the cycle list in order to avoid null pointer exception. We set the source vertex to set minimum distance 0 because this is the starting vertex. Then we iterate through all the vertices, and basically on every iteration we are going to relax all the edges. By the way, we don't have to iterate through as many times, whatever. A bit better solution would be to... Okay, I'm going to have the integer I is equal to 0. I is less than the vertex list dot size minus 1, because this is what we have been discussing in the theoretical section, that we make v minus 1 iteration where the v denotes the vertex list, so the number of vertices, because it's going to be the width iteration in order to check whether there's a cycle or not. But anyways, basically if you iterate through all the vertices, there's not going to be an error, it's going to work fine, but basically there's no point in making the last iteration, so maybe it's a bit better. Okay, and then we iterate through the edges and we relax the edges v minus 1 times, where the v is the vertex list dot size. Okay, if the edge get start vertex get min distance is equal to the integer max value, we just continue, and anyways we pose the question that is there any better solution? So maybe the new distance is a bit better than the previous distance, and that's why we have to update. So set the min distance, the new distance, and have to set the previous vertex, so basically have to update the predecessor. But what's important that after making v minus 1 iterations, so v minus 1 iterations, we have the width iteration, iteration, in order to check whether there's a cycle or not. And if the edge get start vertex get min distance is not equal to the max value and it has a cycle, what does it mean that it has a cycle? That in this iteration the total cost is going to change. So we come to the conclusion that there's a better solution. And if there's a better solution, it means that there has to be a negative cycle. And basically, we just get the vertex from the start vertex, and while this vertex is not equals to the target vertex, we are going to add these vertices to the cycle list. So we keep visiting the vertices that forms a negative cycle, basically. Okay, and then of course we have to return. So basically this is how we are able to track. Okay, this is the hard-coded version. Not so nice. We have the United States of America dollar. Sorry, it's the USD, by the way. Anyways, euro, font, franc, and the Canadian dollar. And this is exactly what we have been discussing in the theoretical section, that we have to take the natural logarithm of the given relative value and we have to multiply it by -1. So basically we have to negate it. So basically with this not too smart code, I created the graph and construct the edges and the vertices, and basically we just have to run Bellman-Ford algorithm on this graph. And if there's a negative cycle, it means that there is an arbitrage situation. What does it mean? That we are able to make riskless money. Okay, so let's see. We have to save it. And yeah, arbitrage opportunity detected. If we convert United States of America dollar to Canadian dollar, then Canadian dollar to euro, and of course euro back to the United States of America dollar, then we are able to make riskless money. So basically I think that, okay, of course if you would like to do high frequency trading, of course you are not going to implement Bellman-Ford algorithm, and you are not going to implement it like this, I'm sure. But I think that the theory is quite important and quite interesting, that we are able to use Bellman-Ford shortest path algorithm to detect arbitrage situations. And most of the times I think there are several counterintuitive situations when we are able to transform a problem into a graph, and we are able to use these kinds of graph related algorithms, shortest path, depth first search, breadth first search, strongly connected components and so on, in order to get the result of the original problem. That's about arbitrage detection implementation. Thanks for watching.